All right, welcome back to another calculus lecture. So in today's lecture, we're going to talk about how you actually find the antiderivatives, these things you need to apply the fundamental theorem of calculus. So we've spoken a lot up to this point about what the integral represents and how to sort of think about it and what the fundamental theorem represents and how to interpret this. But now we're actually going to get into the real meat of actually doing these calculations, which is computing these antiderivatives. So before we sort of get into it, let's maybe introduce a little bit of notation that's common for these sorts of problems. So notation. So the indefinite integral, as opposed to the definite integral, which we've already seen, that's just the integral that we've been writing. The indefinite integral of f of x, which we denoted by the integral without any limits of integration, so I don't put any numbers here, an integral sine of f of x dx. Let's see, the indefinite integral means the general antiderivative of f of x, where an antiderivative is just something that you can differentiate to get f of x. Okay, so this notation just means compute the general sort of object that when I differentiate it, I get f of x. So maybe we'll do an example of that. Switch colors here. Example. So suppose capital F of x is such that capital F prime of x is equal to little f of x. So capital F of x is an antiderivative of little f of x. Then the indefinite integral here, what this means is that the indefinite integral, this is equal to capital F of x, because this is an antiderivative, and then the general sort of antiderivative is I can move this around by any constant c. So where c is any real number. And the reason this is true is because if I differentiate this side, the right-hand side of this equation, capital F of x differentiates to little f of x, but then the derivative of c is just a number, so its derivative is 0. So the derivative of the right-hand side here is precisely this little f of x. And so when we talk about an indefinite integral or computing the most general antiderivative, we mean compute this object where really you compute an antiderivative where the constant is 0, and then you just write plus c afterwards. Okay? So yeah, and we'll talk a little bit more about that later. So now that we've got this notation, let's go ahead and just list down a bunch of antiderivatives. Okay? So we'll just start making a list here. So the power rule, sort of one of the first derivatives that we learned, well, the antiderivative is fairly straightforward. So the antiderivative of x to the n dx is equal to, well, what does the normal power rule say? The normal power rule says that if I wanted to differentiate x to the n, I move the n down, and then I subtract 1 from the exponent. Well, now we just want to do that in the reverse order. So let's add 1 to the exponent, and then divide by the new exponent. So this is going to be 1 over n plus 1, x to the n plus 1 plus c. And here n, although we typically think of n as a natural number, n can be any real number except negative 1, because notice if it was negative 1, we'd have like a division by 0 here. So where n is any real number with n not equal to -1. And remember, the case of -1 was a sort of special case when we did the power rule, or the when n is equal to the new exponent here is equal to 0, we had sort of special cases for that. So maybe let's talk about that. So logarithms. So the antiderivative of x to the -1. So what do I do in the case when I do have this n equal to -1? Let's recall that this equals just 1 over x. This to the power of -1 just means this. The notation is just two different notations to reflect the same thing. So the antiderivative of this is the natural log of x. Because remember, when we differentiate the natural log of x, we get 1 over x. So when you integrate 1 over x, you get the natural log of x plus c. And technically, we should say this is the absolute value of x, because you can integrate 1 over x when x is negative, it's fine, but you're going to get a negative for the in front of the natural log, and so you're going to need to take the absolute value of x here. Okay, so that's the general antiderivative of 1 over x. So let's see. There's one that's fairly easy, exponents. So the antiderivative of e to the x, well, we know that when we differentiate e to the x, we get e to the x back, nothing changes. So the same thing happens when we integrate. So this is e to the x plus c. Again, c here being any real number. And more generally, if I had a to the x dx, this is equal to 1 over the natural log of a to the x, where a is a positive number. So if I want to integrate any power like this, maybe not e to the x, but just any power at all, or any base at all, then I just divide by my natural log of a instead of multiplying it like I do when I do the derivative. Okay, so there's a lot of symmetry happening here, and that's because you're just doing the same process but in reverse. So power rule, logarithms, exponents. I guess we can talk a little bit about the all the trig integrals here. So trig integrals, and there are a few of these. So the antiderivative of sine of x dx. Well, remember, when we differentiate sine of x, we get cosine of x, and when we differentiate cosine of x, we get negative sine of x. So in order to integrate sine of x, I'm going to get negative cosine of x plus c. And likewise, the integral of cosine of x dx is just sine of x plus c. Now, there are a few more of these. So if we have the integral of secant squared of x dx, remember that when we differentiated tangent of x, we got secant squared. So this is going to give us tangent of x plus c. And then likewise, the integral of secant of x tangent of x. This is just secant of x plus c. And then I've run out of room on this page, so we'll continue these last trig integrals on the next page. So lastly, there's the antiderivative of cosecant squared of x dx. And this is going to be just in the same way that we had the negative coming out when we integrated sine. The same thing happens here. So this is going to be negative cotangent of x plus c. And lastly, the antiderivative of cosecant of x cotangent of x dx. This is equal to negative cosecant of x plus c. Okay, so these are all of the antiderivative rules that we need to know. The astute student of you will realize that there are quite a lot of functions that I haven't indicated how to compute the antiderivative of. So, for instance, let's see. So, but how do we compute something like the antiderivative of the natural log of x? I certainly didn't say how to do that. We can differentiate natural log of x, but integrating it is a little bit tricky. And if you want to know how to do this, take Calc 2. Because Calc 2 is going to be mostly focused on the process of integration. So whereas the majority of this course was focused on derivatives, the majority of Calc 2 is focused on computing antiderivatives, computing integrals, and a bunch of different techniques for computing these things. It is much more simple to compute derivatives than it is to compute integrals. And if you take Calc 2, you will learn that very quickly. Okay? So let's go ahead and do a few example computations. And maybe we'll go ahead and do some where we evaluate definite integrals using the fundamental theorem of calculus. So let's compute the integral from 1 to 3 of x squared plus 2 dx. So here we're going to need to use the power rule. So the fundamental theorem says that I need to find an antiderivative of this, and in fact it doesn't matter which antiderivative I use. Any old antiderivative will suffice, and in fact any antiderivative we see only differs by a constant. And when we write down what this integral actually is, you'll see why the constant doesn't actually matter. So we can take it to be 0 when we do our definite integrals using the fundamental theorem. So let's go ahead and just do this step by step. We'll write down each antiderivative. So the antiderivative of x squared. This is, well, I apply the power rule, so I add 1 to my exponent, and then I divide by my new exponent. So this is going to be 1/3 x cubed plus c. And the antiderivative of 2 dx, this is the antiderivative of, this is 2 times the antiderivative of dx, because constants can come out front like this. But then the antiderivative of, well, really just 1 is x, because when we differentiate x, we get 1, and so when we integrate 1, we get x. So this is going to be 2x plus c. Now, in order to compute this, the fundamental theorem says that all I do is I take my general antiderivative and I evaluate it at each of the endpoints and then subtract. So to do this, we simply say, okay, well, I have the integral from 1 to 3 of x squared plus 2 dx. This is equal to, now I put in my general antiderivative, and there are a number of ways to notate this, but the way that I typically do it is just I write down my antiderivative, and we're free to choose our constant to be whatever we want. So we'll just choose it to be 0 for convenience. And then typically what I like to do is I like to put an evaluation line here that says evaluate this from 1 to 3. And this notation is just meant to convey that we're going to do, we're going to evaluate this at 3 and at 1 when x equals 3 and 1, and then subtract those two. So this means perform this operation. There we go. So there's where I evaluated the function at 3, and then I subtract, evaluating it at 1. And now we just simplify. So this is 3 to the third is 27, divided by 3 is 9. So 9 plus 6 is 15. And then minus 1/3 plus 2. And this is, oh what? This is 7/3. 45 minus 7 is, I believe this comes out to 38/3. But if you wanted, you could just put this in a calculator. No need to do it, you know, get an exact answer like this if you don't want to. So this is how we can do our general sort of computation like this using the fundamental theorem. Notice that if I had chosen my c to be, let's say, 1 or 2, then each of these parentheses would have a +1 because it doesn't depend on which x value I have here. So there would be like a +1 inside of this parentheses and a +1 inside of this parentheses, or whatever constant I chose. But then they would just cancel out because this one would be positive, and the negative here would distribute to the other constant inside and make it negative. And so they would just cancel. Maybe let's just see that, in detail. So also, we could have done 1/3, 3 cubed, plus 2 times 3. I changed my constant, so let's say I chose 5 for my constant. Then this is what happens when I perform the evaluation. There's my +5 that I chose, but then the 5 minus 5 just cancels. So when you're doing definite integrals, it really doesn't matter that that c can be whatever you want. You typically just choose it to be 0 because it's computationally convenient. However, when you do general antiderivatives, when you do indefinite integrals, you need to include this +c. So maybe let's make a note of that. So definite integrals, we can choose c equals 0, but indefinite integrals, if I tell you to compute a general antiderivative, then you need to write down the +c, because you need to tell me that the general antiderivative is any of these functions, but then I can shift it up or down, because that's exactly what this +c is doing. It's just shifting the graph vertically by some amount c. Okay, so this is how to do definite integrals using the fundamental theorem. Maybe let's do an example of just computing general antiderivatives. So compute the antiderivative of e to the x plus cosine of x, the indefinite integral of this. So using what we just wrote down on the previous page, we can say that the indefinite integral of e to the x plus cosine of x dx, just like the regular definite integral, the indefinite integral is linear, so I can split this apart into 2 indefinite integrals, which is what I did up here as well. And this is going to equal, well, e to the x, the antiderivative is e to the x plus c. And then cosine of x is sine of x plus c. Or maybe we'll say c1 and c2, where c1 and c2 are just unknown constants. And typically we don't write this this way because the sum of 2 unknown constants is, again, just an unknown constant. And so we'll typically just say this is e to the x plus sine of x plus c, where c is any real number. Okay, so once you're done computing your antiderivative, you write down the really interesting part, and then you just sort of tack on a plus c at the end. Okay, so that's how to do sort of definite and indefinite integrals using these integration rules. The next thing that I want to talk about is the method of substitution. So, method of substitution. And this is often called change of variables. Change of variables, or u-substitution, and that'll be clear why we call it that in a moment. Just sort of a notational convenience. Substitution. And in order to sort of illustrate this method, I think it's probably best to just use an example. So, example. So let's say we wanted to compute the integral of, let's say, cosine of x times sine of x to the 4th. Any old power will do. Well, we know how to compute the antiderivative of cosine, and we know how to compute the antiderivative of sine, but how exactly do I do it when I have a product of things like this? Well, what we can do is we can sort of reverse engineer the chain rule. So idea, try to reverse engineer the chain rule. Think about how, if I wanted to know what function when I applied the chain rule to it would give me something like this, well, I can use that same reasoning to figure out how to integrate this thing or compute the antiderivative. And the idea is to look for a function that is inside of another function, a function being composed with another function whose derivative appears somewhere else in the integral, in the integrand here. So we want a function that is inside of another function and whose derivative appears in the integrand. Integrand being just the function here between the integral sign and the dx. Because if I think about what the chain rule tells me, if I write that down up here, d dx of f of g of x, this is f prime of g of x times g prime of x. Well, I kind of want a function, g of x, that's inside of another function and whose derivative appears somewhere else in my integral. Well, I can look at this and say, oh, well, sine of x kind of does that. It's inside of this to the power of 4, and its derivative, cosine of x, appears elsewhere in my integral. So let's try and do this. So let's let u equal sine of x. Then what we're going to compute is the differential of u with respect to this sine of x function, or with respect to x. So we know that du dx is equal to cosine of x. And then one of the nice things about Leibniz's notation, this derivative notation, is that it sort of lends itself to saying this. Du, this quantity, is equal to cosine of x dx. Now, this is not exactly what's happened. I haven't really multiplied on either side. It's not really rigorous to say that's what happened. But this du is called a differential, and it is equal to this function cosine of x times another differential. We don't really need to get into that, but you can, if it's more convenient to think about just multiplying by this dx, then I think that's fine to do, at least on an intuitive level. So I've computed my new differential with respect to x, so du is equal to cosine of x dx. Well, now I just take my integral and I rewrite it in terms of all of these new symbols that I've written down. So the integral of cosine of x times sine of x to the fourth dx, this is equal to, well, cosine of x times dx, that's just du, that's my new differential. So, and then sine of x is just u, so this is really just u to the fourth, sine of x to the 4 is just u to the 4, and then times du. And look at that, now this is an integral I know how to compute. The u here, that's the variable I'm integrating with respect to, so I can simply say this is 1/5 u to the 5th plus c. And then, in order to finish the problem, I put back in what u was. So this is 1/5 sine of x to the 5th plus c. And we've computed this antiderivative. Okay? So this method gives us a way of computing certain integrals that we otherwise wouldn't quite know how to handle. Maybe let's do another example just to get our feet even more wet. So this time maybe let's do a definite integral as well. So let's compute the antiderivative, or the integral from 1 to, 4 of 2x times the square root of x squared plus 1 dx. Okay, well, I look at this and I say, well, I don't quite know how to integrate that with just the tools that I have, but maybe I can use the method of substitution, the method of u-substitution, which is why we use the u here. So let's let u, and we want to think about a function that's inside of another function whose derivative also appears in the integral. So I choose u equal to x squared plus 1 because, boom, there's its derivative. So u equals x squared plus 1. Then du, the differential of u with respect to x, this is 2x dx. I just differentiate this and then write dx afterwards. And now what I can do is I can, evaluate the indefinite integral here and compute my general antiderivative and then switch back from u at the end. Or I can really just change my limits of integration in my integral. So if we want to do that, we simply say that u here, u is a function of x. So if I evaluate u at the upper and lower limits, these are values of x for the integral. So u of 1 is just 1 squared plus 1, which is 2. And u of 4, the upper limit, this is 4 squared plus 1, which is 17. So now I just rewrite my integral. So the integral from 1 to 4 of 2x times the square root of x squared plus 1 dx. Now I just put in all the information that we have. So the integral now, instead of going from 1 to 4, it's now going to go from 2 to 17. Let's see, I have my 2x dx here. That's my new differential. And then x squared plus 1, that was u, so I just have the square root of u du. And now I can apply the power rule because this is just the antiderivative, or I'm sorry, the integral from 2 to 17 of u to the 1/2 du. This is going to equal, what do I do for the power rule? I add 1 to the exponent, and then I divide by that new exponent. So if I add 1 to 1/2, I get 3/2, and then when I divide by 3/2, I just flip the fraction. So I'm going to get 2/3 u to the 3/2 evaluated from when u goes from 2 to 17. And so this is going to be 2/3 times, because I'm just going to factor the 2/3 out right now, this is going to be 17 to the 3/2 minus 2 to the 3/2. And if I was better, I would have chosen more convenient numbers to use here. But this is just, it's a number, and you can put this in on a calculator. So this is equal to something. Use a calculator. Calculator, not to be confused with calculus. Okay, so not only can we just compute indefinite integrals, we can also use this method when we're computing definite integrals, because we can also change our limits of integration from our change of variables here. Okay, so that's everything for this video. In the next video, we'll start the few applications of the integral that we're going to do, and then a few lectures from now, we'll be pretty much done with the course. So see you all in the next lecture.